Hi there, welcome to your really short tutorial on solving problems involving the acceleration due to gravity. So I'm going to walk through a problem with you here. You should take notes along the way so you have a good example of how to solve these problems. And there are just a couple of particulars that you need to pay attention to in order to be successful solving these types of acceleration problems. And the first thing to note, of course, is that the acceleration due to gravity is negative 9.81 meters per second squared. Negative because anything that is down is negative and anything that's up is positive. Just like we say that anything that goes east is a positive number and anything that goes west is a negative number. So because this acceleration is always down to the center of the earth, we give it a negative number. And you use that negative number when you do your problem. Here's the problem that we'll do today for your tutorial. And it goes like this. How fast will a penny be traveling upon impact when dropped from the CN Tower? Okay, so I got a chance to actually try this summer. I didn't get very far because I was quickly accosted by gentlemen in some fancy uniforms as I climbed up the CN Tower in the usual way, and then I tried to throw something over the top of the CN Tower. I encourage you to try this. However, don't be surprised if you end up with a hefty fine, as it's pretty well policed. But I was able to get some information that will help us. And while this tower is 553 meters tall, I was able to time how long it took from the very top to the very bottom for a penny to fall. And I use a penny because it has such a small surface area. The amount of air friction acting on it is negligible. And for all of our problems, we pretend that there is no air friction, and when we're modeling what has actually happened. And so the time it took for this penny to fall, and it would take the same amount of time if it were a cat, if it were a penny, an object launched or dropped from the top of the CN Tower would take about 10.5 seconds to reach the bottom. That is a lot of air time. Okay, so we know the acceleration due to gravity. This object's in free fall, so we know it's accelerating. You always have to remember that. Delta t is 10.5 seconds. And because it's dropped, the initial velocity is 0 meters per second. And that's important. If you ever see in a problem, it starts from rest or it is dropped, you know that the initial speed is 0, and as soon as you let go, it is 0 meters per second for a moment in time before it starts to accelerate. And we're asked to find the impact velocity, and we can call the impact velocity v2. How fast is it actually going to be traveling when it hits the ground? And then we can ask all those questions. Could it actually embed itself in somebody's head at that velocity? All of that stuff. So here is my diagram, and I've listed all my variables, what I know and what I want to find out, and this is what I want to find out today. Next is E, which equation is going to allow me to do that. And we're going to use our old buddy, A equals V2 minus V1 divided by delta T. Then we can plug in our numbers. Well, we know acceleration, it's a negative number. And it's important you put it as a negative number because directions, east, west, down, up, that way, this way, when we use math to model, we have to convert those name directions into a number or value direction. And we do that by saying anything down is a negative number. So it's negative 9.81. It's not accelerating upwards. V2 is what we are trying to solve for. And V1 is 0. So we can just write that in there, 0. I love zeros. divided by the time, which is 10.5 seconds. Now we have to rearrange this bad boy so that we can isolate for our desired, and that of course is V2. So let's rearrange this guy. We want to get rid of the unit there. Want to get rid of the 10.5. The V2 is stuck to the 10.5 through division, so we're going to do the opposite function to isolate it. And whatever we do to one side, we have to do to the other side. So these guys cancel to 1. And if I rewrite this formula just so it looks a little nicer, we have 10.5 multiplied by negative 9.81. All right, so it looks like it's going to be about 90, but I'm going to use my calculator here. So 10.5 times negative 9.81 is negative 103.005 meters per second. Okay, so first thing, and you got to pay attention to this, the negative sign means that it is heading downwards. The velocity is in a downwards direction, so that agrees, and that's why we include the negative sign in the acceleration. Not quite done though, we have to observe some siggy-diggies. So when we look at our data, we've got 3 significant digits there, 3 there, so our answer can have 3. So I'm going to round this off, so V2 equals 103 meters per second, and because it's a velocity, down. Now look at this, because I've said down, I don't have to put the negative sign. But when I first wrote the number up here, I didn't have a direction, but I did have the negative sign. The negative sign is in place of a direction. So you could say V2 equals negative 1.3 meters per second, or you could say 103 meters per second down. So there you go. That's how you solve a problem involving free fall. The first trick is to identify when a free fall is being engaged. Secondly, call the acceleration negative as it's headed downwards. And then it's just straight up DLESS method problem solving. All right, take a look after the video for a couple of practice problems I'd like you to try out. Let me know if you have any problems. We'll talk to you soon.